difference in few minutes. Then followed by, there is a layer-wise theory that I developed. And also there are other people who have contributed to the layer-wise theory, including Murakami, for example. So anyway, I will talk about these two theories in the next few slides. So both of these theories are detailed in my book, and those who have a copy of this book, either in your departmental library or university library, you may consult them. So I will begin with the kinematics of deformation of the third order shear deformation theory. And so then I talk about how the displacement field is derived, and talk about the trains, and then equations of motion. And then I'll look at some numerical results to show how the third order theory does better than the first order shear deformation theory. Then the second part of this first lecture involves layer-wise theory. Again, I will give the basic idea of the layer-wise theory. Then I'll talk about the equations of motion and some basic results. By the way, it should have shown the displacement and strains as well. So then I close with the summary of the lecture. So let us begin with the third order shear deformation theory. So if you look at, this I'm putting different color layers. If you think of a plate or shell, through thickness, if it is a laminated structure, you will have different layers. There could be as many as 40, 50 layers. Each layer could be different material, different thickness. But in real world, most of the manufacturers have same thickness layers, but we lay up them in different orientation. So-called lamination scheme is different, which amounts to be equivalent to saying that each layer is different material because of the orientation is different. So when we use the standard theories, we assumed in the classical laminate theory, we assumed that the transverse line, one that I just showed in red, is one straight line. So you remember yesterday I was talking about straight lines remain straight and inextensible, and then they rotate such that they remain normal to the mid-axis during the deformation. So that makes the theory little bit of over stiffening the structure. That means we are modeling the structure stiffer than it is. As a result, we under predict displacements, over predict stresses, and especially buckling loads. So these are not very conservative because we know the structure will fail before your theory says it will fail, and that's not good. If anything, we want the theory to predict that structure fails before it actually fails. So that gives a little bit room for, what you call safety. So the higher order theories, such as the first order shear deformation theory, what does it do? It creates that broken line. I just put it there. So it expects the shear strain to be constant and shear stress to be constant within each layer. Okay. So whereas the third order theory is going to do that. So that means it doesn't have to remain straight line. By the way, this is an exaggerated picture. Okay, obviously the layers don't deform that much, but the point here is that each layer being relatively of different stiffness, they will actually undergo different amount of strains in each layer. So that is why it cannot remain a straight line. It has to become a piecewise linear or quadratic variation. So the third order theory has better representation of the true deformation in a laminated structure. So that is the thinking that made me to develop this theory. This theory was published in 1984 in Journal of Applied Mechanics. And I think I checked today, it has 3,560 citations. This is my I mean, I have a lot of citations for my books and others, but this is the one paper that has the most citations. So the idea of my third order theory is to assume that the displacement field through thickness varies cubically, so that the shear strains are quadratically varying, so also the shear stresses. And then I make the sigma xz and yz, which are the in plane surface stresses, that so that the stresses that are occurring between the layers and also on the top surface and the bottom surface. So I apply the condition that they should be zero at the top and bottom, but not in between the layers. Okay. So the theory simplifies a bit, and I'll explain that in more detail in few slides. So this is the general idea now. Okay, so if you see the displacement field that I'm showing at the bottom of the slide is the general third order theory. So what I mean by general means every coefficient in the expansion of the cubic term in z coordinate are independent. U, phi x, theta x, lambda x. Each one of them are independent unknowns. So also in the next line, v, phi y, theta y, lambda y, and then w. So w doesn't have any expansion, although you can include expansion in w also, and we have done that before. So now if you count the number of unknowns, you see that there are 9 unknowns. U, V, W, 3, and then you have Px, theta x, lambda x, and Phy, theta y, lambda y, 6 more. So total 9 unknowns. So what I do to create this so-called third order theory of ready, I eliminate some of these unknowns by imposing that the shear stresses at the top and bottom should vanish. So that is what I'm going to show you in the next slide, okay? So before I get there, this is one more time showing the through thickness of this plate. So before we were using straight lines remain straight, both in classical plate theory and first order shear deformation theory. But now we are saying the straight lines can become curves, whatever is dictated by the lamination scheme, but we are saying each layer does not strain proportionately, but they can change depending on the individual stiffness. So that really requires you to model strain in each layer to be different. And that amounts to saying the straight lines cannot remain straight. Okay, so, and you don't see anything new on this slide other than this picture showing you the transverse line became a curve now after deformation. So let's go to the actual displacement field that you saw on the previous slide. Now what I do, I make sigma xz and sigma yz both to vanish at top surface and bottom surface. Top is plus h over 2. That means z is equal to plus h over 2. And bottom is z minus h over 2. So that makes, because these stresses are only related to the shear strains, it implies the shear strains also must vanish at the top and bottom. So when you apply these conditions, what happens to the third order theory coefficients is the following. It immediately shows that, so you see that gamma xz, and if it has to be 0 at the top and bottom, it immediately says psi x has to be identically 0. And whereas theta x should be related to phi x plus dw dx. So what did we do? Out of 9 parameters, 4 of them are related to the remaining 5. So that means we will have only u, v, w, phi x, and phi y, just like in the first order shear deformation theory. However, this has the cubic variation. So the number of unknowns in the are still same 5 as in the first order theory. Okay, so this is the first order theory displacement field. So you can count U, V, W, Px, Py are the only 5 unknowns, because these expressions now in terms of the same quantities as before here. So total are 5. But one thing that happens is the third order theory in terms of looks, it has first order kinematics up to here. If you throw the third order terms, that means coefficients of z cube, you will get the first order theory. But it also has indirectly the first order classical plate theory kinematics, because it has dw dx, dw dy. Okay, so as a result, this theory will have different features which tends to mimic both the classical plate theory kinematics and first order theory kinematics. So now we take this displacement field, compute the strains. I mean, of course, you can have nonlinear strains if you want, but the general picture that I'm showing here, that the in-plane strains will be cubic all the way. It will have the extensional strains, then first order bending strains and third order bending strains. Okay, and then the quadratic variation of the shear stresses. And this is very nice, because before in the first order theory we have only this part constant, and we required to have shear correction factors because we know the shear stress is not constant, especially in composites. So now we have the facility or ability to represent the shear stresses quadratic through the thickness. And as a result, you don't need shear correction factors. So the third order theory kinematics is much better, more close to the reality than classical plate theory or first order theory. So the rest of the story is very standard. We can go and compute the strains, including the von Karman type nonlinearity, which I showed here, dw dx whole squared, means we are assuming the strains are small, but the rotations are moderate. That means if you have a plate that is bending, so there is a rotation about x-axis, rotation about y-axis. So these rotations could be moderately large, and that's what von Karman nonlinearity brings in. And so this is the third order theory with von Karman nonlinearity included. And so I'm just showing you a result. I can, show all the details of the equations, but you will just see the lot of expressions, but you can see them in the book. So, but I want you to see the benefit of using third order theory. So here I'm plotting the deflection in non-dimensionalized and versus the A over H. A is the length of the plate. In this case, length and width is the same. A and B are same, means a square plate. And the thickness is H. So when A over H goes to 50 or 100, it is really thin plate. Whereas it goes toward 20 or 15 or 10, it is relatively thick plate. So you can see the classical plate theory, because of the way it is non-dimensionalized, as you change the thickness, the deflection, non-dimensional deflection doesn't change with A over H ratio. Whereas the deflection predicted by the first order shear deformation theory, third order shear deformation theory, or exact elasticity theory. For this problem, you can cook up the 3D elasticity solution also because of the special case of simply supported. So you can see the 3D elasticity solution is the solid line. And the third order theory comes very, very close to the 3D elasticity, followed by the first order shear deformation theory. Okay, so you might say, oh, first order theory is also doing very good. Of course it does. Okay, so it is most popular theory that we use, which is also in commercial codes. But when you want to omit or not to worry about shear correction factors, and also you want to predict the shear stress through the thickness accurately, the first order theory cannot do that because it only says it's a constant. Whereas the third order theory will show that, and I'll show that picture in a moment. But you can see for this problem, the deflections predicted by both first order theory and third order theory are very good in comparison to the elasticity solution. But stresses is a different matter. Okay, so here is a little bit complicated looking, but I will explain to you. So if you look at, this is a 4-layer laminate, 0, 90, 90, 0. So it's a symmetrically laminated 4-layer plate. So you can think of through thickness minus 0.5 to plus 0.5. This is the normalized thickness. So the first layer is here, then middle layer, 2 of them here, because 2 of the 90 is like one single layer, right? Except double the thickness. And then one more layer at the bottom. So what I'm plotting here is sigma xz. And sigma xz, and this is of course for a thick plate. If it is not a very thick plate, then it will be just parabolic. Okay, if it is really not a laminate, it would be parabolic variation of the shear stress. But since it is three different layups, 0 and double the thickness, 90 degree, and then 0. So the shear stress would be different in the different layers. The middle layer will have one variation, and the bottom and top will have a different variation. So let me explain what these curves are here. So the classical plate theory cannot give you any shear stress at all unless you go and use 3D elasticity equations to back out the shear stress in the classical plate theory. And that is what we call through equilibrium. Okay, so that is only we can do for academic problems. We cannot do in general because solving 3D equations, with the approximate stresses that we obtain from the plate theory will not be very accurate, but in any case, it shows that the CLPT solution is this at the top and bottom here and in the middle. Okay, I could have put a different color. So that shows a big jump here. See this? And whereas the first order theory using the constitutive model will give you this constant in the top layer and this constant in the middle layer and this constant in the bottom layer, because that is all it can do. But if you also use equilibrium equations to solve for the shear stress using first order shear deformation theory, then it will give you slightly different result as shown here. And it looks better, of course. And whereas the third order theory or those circles and the 3D elasticity theory comes very close to it. Okay. So you can see the shear stresses predicted by third order theory are much better than any of these other theories. And equilibrium is really a very special thing that we cannot routinely use it. In commercial codes, we never use it. We only compute the shear stresses using the constitutive equations, in which case classical plate theory will give 0 shear stress, and first order theory will give constant in each of the layers. Okay, so which would be much different. So if you were to really predict failure at the interface, in the case of the first order theory kinematics, there is a jump again. You see that. So it doesn't know, failure theory will fail to know which way you have to employ because it is showing at the interface 2 values of the stress. So it's not going to work well. You have to have a unique value. And that is what the third order theory does, no matter how you get it, whether through equilibrium or constitutive equations. Both of them are very close to each other. You can see that. Okay. Now I want to show sigma yz. Okay, you are listening to me, but you have to remember where these stresses are occurring. So imagine that you have layers of laminate. So when you look at interface of two layers, that is where the shear stress sigma xz and yz are. And in fact, there is a sigma zz also. Three stresses on that plane. So if the sigma xz exceeds the allowable for the material glue that is connecting or gluing two layers, then it will delaminate. And whereas if it exceeds sigma xz or yz allowable, then it will also delaminate by shear. Okay, so it is important that we predict these interlaminar stresses very accurately. In fact, laminates fail mostly in interlaminar stresses. They don't fail in extension because fibers are very strong. Okay, so it becomes very important to have very accurate theory for predicting the interlaminar stresses, which is sigma xz yz. So now I'm showing sigma yz. So here you can see the third order theory through equilibrium and constitutive model are here. So whereas the other theories are really under predicting the stresses. Of course, in the case of first order constitutively, you will get only constant in each of the layers. But if you use equilibrium, they will give something, but they're still considerably in error compared to the actual values of the shear stress in a laminated structure. So this is the benefit of third order theory. It predicts the interlaminar stresses much better. The displacement field predicted by all theories are not that much of a difference. It's not a major issue, but it is a big issue in predicting the interlaminar stresses. So that completes the coverage of the third order theory. Now I want to talk about a little bit about if you make the plate functionally graded, and I've showed these two graphs before, then these AXX, DXX, and BXX will depend upon the power law index. Of course, this is a specific form of the material variation. So this is not a laminated structure now. That means in lieu of layered media, you have a single material, but that material is varying through thickness. So that way you really get rid of the any kind of stress concentrations. That is the main idea of these FGMs. Doesn't mean we always use FGMs. We still use composites, layered composites in many structures, but this is another area that has come up in the last 2 decades. So, and I'm just showing you the results of that functionally graded material. You will see that depending upon the value of n, so if you n equal to 0 means it's not functionally graded. It's just a one material model. Then you will have very stiff structure here because the E2 is much larger than the E1. E1 is at the bottom and E2 is at the top. And as you increase the n, of course, it will become more flexible. And so you can see it goes from 0 to all the way to the 10. 10 is the most flexible. So this is just a deflection from the one point to the one end of the plate to the other end. The center will have the most deflection, of course, for a simply supported case. And you can show if you do the same thing for nonlinear, these deflections would be reduced because of the stiffening effect due to the nonlinearity. So I'm not showing them, but we have those results as well. So now I want to talk about the layer-wise theory. So what is the limitation of any of these theories? Classical, first order, third order, is that they all assume variation of displacement field through thickness to be continuous. That means if you take a point between layers through the thickness, okay, so you have layers here, okay, or think of many layers here. At any point through thickness, including at the interface, you have one unique value of displacement. And but not only that, because of continuous variation, even the shear strains that you compute will have continuous strains. But we know since each layer is of different stiffness because of their orientation, fiber orientation, they should have the ability to stretch or compress independent of each other. And that is not allowed in the single layer theories. No matter how higher order you go, you're still assuming that the strains are going to be continuous. And whereas the stresses we know are discontinuous, especially sigma xx, sigma yy in each fiber. But what we need is the continuity or balance of the interlaminar stresses. So the physics or engineering tells you that if you open up two layers, what occurs on the top surface of the layer at the bottom should be exactly same as at the bottom of the layer above it. So these are shown in broken line. So in magnitude, they should be exactly same, but opposite in sign. This is Newton's third law, right? And that cannot happen because of the shear stresses, shear strains being continuous. So this gave rise to the idea, because of my background in finite elements, I said we can bring the discontinuous strains because finite elements very naturally allows the derivatives to be discontinuous, right? Because between elements. So now think about that and say, so here I'm enlarging the thickness. This line is now here, all the way up here. So between these white circles is a layer. Okay, so many layers here. So I'm saying each layer, this line will, so this is of course an exaggeration, will change its variation. That means it will have different displacements at different nodes through the thickness. So this is very similar to third order kinematics, but it is piecewise now. Whereas in third order theory, we assumed this is a continuous curve. But now we are, if it is continuous, then you cannot have the derivative with respect to z is continuous because it's a continuous variation. There's no discontinuity there. So here we are saying layer-wise we create a theory that will allow the layer-wise representation of the displacement field. So that is this expression here. So that means UVW. Now these UVWs are the 3D elasticity displacements in X, Y, Z direction. They are expanded in terms of nodal values, and nodal values are at the interfaces. So for example, if we take ith node will have 3 coordinate displacements along the 3 different coordinates in X direction, Y direction, Z direction. And those will be called U sub I, V sub I, W sub I. But those are only functions of X and Y. Because I'm explicitly representing the kinematics through the thickness, that is the Z coordinate. So what you see from this expansion, we are separating X, Y from Z. In 3D elasticity, we don't do that. But here, we are allowed because of the laminated structure. See, I cannot do this if it is an arbitrary solid. But we don't have an arbitrary solid here. It's a very structured solid. That means it is a layered media put together. All the layers are nicely laid up, right? So it allows us to separate the XY coordinates with the Z. This is a separation of variables. Once we do that, we reduce the 3D elasticity theory to two-dimensional because we can explicitly integrate through thickness. So the resulting equations are going to be in terms of ui, vi, wi in two dimensions, x, y coordinates only. So layer-wise theory is indeed 3D elasticity, but except we have created a structure that separated the thickness direction from the in-plane direction. Okay, so that is what I'm showing here. Okay, so this a typical interface will have three displacement, much like in a 3D elasticity. But the elements that we are going to have, finite elements here, will be instead of arbitrary three-dimensional solid, it would be one thick solid element with the nodes having three displacements at each node. So it's very similar to 3D, but the thickness is already eliminated. So this requires a little bit of thinking on your part, although I'm trying my best to explain. So when you finish with the equations of motion, see, they look exactly like plate equations, except there is a superscript. Because these equations are valid for any typical interface. So that means there are many interfaces. So if you have 50 layers, there would be 51 interfaces, including the top and bottom. And 51 interfaces times the number of elements you made in the plane times 3. 3 are the displacement degrees of freedom. So the number of unknowns in the structure will be exactly same as in 3D elasticity. So you don't reduce the number of unknowns, but the evaluation of the coefficients, stiffness coefficients, becomes very fast because we reduced it to 2D. Okay, the unknowns remain the same, but the structure changed so that the speed of computation is much higher. The number of coefficients that you have to evaluate to generate the stiffness matrix are much, much less than a 3D elasticity. So here I'm showing you, for example, if you see 3D elasticity element here, this element shows cubic variation in the plane and linear variation through thickness, right? That's what you see there. Whereas this one is a quadratic variation through thickness and quadratic variation in the XY. You see 3 nodes in X and Y direction means quadratic, and 3 nodes through thickness. So here all 3 directions are quadratic. Here one direction is linear, other 2 directions are cubic. So in the layer-wise theory, what happens is, since we eliminate the thickness by assuming the linear variation to match this, and then you have the cubic serendipity element in the plane. And here, quadratic through thickness and quadratic in the plane. So since they are separated, thickness and in plane, there is no aspect ratio issue with thickness. That means you will not have thickness locking because thickness is gone in the computation. Once you have this variation through thickness, it's integrated out. You can even do it exactly. Okay, so the elements are all going to be two-dimensional. And so this combination will give you this element of 3D elasticity. This combination will give this element. So now we have much flexible way to create. We can use all kinds of approximations in plane and through thickness independent of each other. Okay, so that is the nice thing the layer-wise theory brings to the table. Now I'm going to just show you one example here. Here is again 3-layer laminate, 0, 90, 0, for example. So I'm showing one quadrant of that. And if you look at that from 3-dimensional point of view, you think of using 3 rows of elements through thickness, and then there is a 2 by 2 mesh in the quadrant, right? So each element here will have, if you think of linear here, so the 3D element would be linear through thickness and quadratic in the plane. Okay, so that kind of mesh can be generated by layer-wise theory with this. So each layer, 3 layers, will have quadratic variation, and then in plane element would be 9-node element. Okay, so this combination will give this mesh. So if you use this kind of thing, so this table shows, I want you to understand the facility here. If you think of a 3D finite elements, it will require 1,116,000 multiplications to generate the stiffness matrix, 677,000 additions, and 511,000 assignments. Assignments means A equal to B, B equal to C, that kind of assignment. Whereas if you use the layer-wise theory, corresponding layer-wise theory, it only requires 423,000 multiplications, almost nearly 1/3. Here 1/2 and 1/5. So you can see similarly for that second case where the 3D element, where you use quadratic in the thickness and quadratic in the plane, again you see it takes 1,182,000, whereas the layer-wise theory only takes 284,000. So this tells you computationally layer-wise theory takes less computational time, but produces exactly same results as 3D because it is 3D. It has the same displacements as three-dimensional solid. However, the layer-wise elements are only good for laminated structures. You cannot use them for arbitrary solid because there are no layers. So I'm showing you the results of sigma XX. So this is a thick plate. So through thickness, 0 at the bottom, 0 at the top, middle layer is 90 degrees. So 0 degree means fiber is taking the load. So you can see the stress in the fiber is going to vary according to this equation as predicted by exact 3D elasticity. Same in the bottom layer. And the middle layer take no stress at all because they are not in the direction of the stress. So they are in the 90 degree means fiber is screen, whereas 0 degree means they are along the in plane direction of the stress, sigma XX direction. So if the structure is very thin, what happens is all 3 layers will have one continuous straight line going from bottom to top here. For a thick laminate, that will not happen. Each top layer and bottom layer will experience more stress and middle layer has no stress. So whereas the first order shear deformation theory and classical plate theory predict linear variation because that's what we have in the displacement field, and they are doing the best they can. But in the process, what is it they are doing? They are approximating this curve in average sense. Okay? And in the process, they also predict a jump at the interfaces. So whereas the third order theory, or sorry, layer-wise theory will do very good job, and then it goes to 0, okay? And then, of course, by the way, this jump is expected because sigma XX is not necessarily continuous, mechanics sense, and because it's in this direction, not in this direction. And that would have been the sigma ZZ and sigma XZ and YZ, which should be continuous. But the sigma XX is not continuous at the interfaces. Okay? So what I was commenting earlier is this jump is in the wrong direction compared to elasticity solution. See, jump is in this direction, whereas the 3D elasticity theory result is this solid line. Okay? So you can see the layer-wise theory does, I mean, of course, it should do exactly the same as 3D elasticity, as I said several times. And depending upon what kind of mesh you use through thickness, it may vary slightly, but here both meshes did extremely well. They're right on the same curve. So now I'm showing the solution predicted for sigma yz. So you can see the exact 3D elasticity solution for sigma yz, because there is no jump now. So is shown here, and the layer-wise solutions are also right on the elasticity solution. Whereas FSDT through equilibrium, CLPT through equilibrium, they will give these, but they are going to be in error. And CLPT is much more error than first order shear deformation theory. So whereas if you use constitutive law, they will give constant value through each layer. That would be a lot more in error than third order theory or layer-wise theories. So you get the idea that layer-wise theory is much more accurate, but it is computationally more expensive than single layer theories, but it is still cheaper than three-dimensional elasticity. So I have done quite a bit of work in this area to say that in general, you don't use layer-wise theory everywhere in the laminate. You use only where you think there is a three-dimensional state of stress. Elsewhere, you use the 2D elasticity type single layer theory elements. That means first order shear deformation theory everywhere except in three-dimensional regions where 3D state of stress exists. There you will put the layer-wise theory. So we have done those kinds of things, and you can read in the book more. So that completes the discussion of the layer-wise theory. So I will close this lecture by saying a few things about the third order theory. It removes the normality and straightness assumptions, which are included in the both first order theory and classical plate theory. So it represents the deformed transverse lines to be cubic through the plate thickness. So as a result, it represents the transverse shear stresses to vary quadratically through the thickness, and therefore it does not require shear correction coefficients. And this is something people like it because otherwise they don't know how to get the shear correction coefficients. And shear correction coefficients, normally people use some fixed number, but it is very well known that they do not, they are not constant. They depend upon boundary conditions and the lamination scheme. And that is not required in third order theory. Of course, layer-wise theory is indeed a 3D elasticity theory, but exploits the layered nature of the laminate to simplify the governing equations, and it has no thickness aspect ratio restriction. That means you can use in-plane elements. They don't have to match in terms of aspect ratio with the thickness direction, because thickness direction is independently modeled. Okay, that completes, and I want to just say we have looked at both third order shear deformation theory and layer-wise theory in this lecture, and I tried my best to explain the main idea behind each of them. Okay, I'm here to give any, take any questions and explain anything further.
I think it's very clear. So if you have questions, please let me know, or you can ask Professor Reddy directly through your microphone, or you can send a message. Professor Reddy, I have one question. So
please,
when you use the layer-wise theory, so do you have any, you use this theory and to build the FEM, right? So do you have any problem, the shear locking problem? Because for the traditional finite element, shear locking
that's
is a big problem.
Very good question. Okay, so two comments. One comment, the third order shear deformation theory has still locking, but it's quite a bit less.
It's better than the traditional. Is it right?
Because it's not layer wise, and whereas the layer wise theory has no locking at all. because we are not doing anything specific to represent the shear stress differently. It's a 3D elasticity. See, whereas in the plate theories, shear deformation theory, we are expanding the displacements in different direction, different ways. So there is a issue with the shear strain, which has the rotation function undifferentiated and then transverse deflection differentiated. Then we force both of them to be linear through thickness or linear through the in plane, right? So when
Yes.
you say the rotation is linear and the transverse deflection is linear, we know that cannot be true because rotation is like a dw dx. And so that inconsistency in our interpolation, not in the theory, in our choice of interpolation causes the locking. And in fact, I've shown if you increase the order of differentiation, interpolation for W, the locking will go away. You don't need to do that. But people who are computationally oriented, they don't want to increase the interpolation degree because they want a cheaper element. So they found a way to eliminate the locking by using reduced integration. But reduced integration has side effects. It might bring what you call spurious modes.
Hourglass.
Yeah, other hourglass modes or other things. So that is why I think we should try to eliminate these kinds of fixes. We should not play with artificial way to get rid of locking. We should do genuinely put a right kind of interpolation for each of the variables as dictated by the governing equations. Then you will not have locking. But that means you have to pay a little bit more. So there is no pre-lunch. You have to pay if you want to get more accurate results. Whereas coming to the layer-wise theory, there is no shear locking. Okay, so
Thank you.
so that
Thank you.
is
Thank you for your answer.
right. Any
Any
other
more
question?
questions?
Yes. You want
Any
me to
more
go to the
questions?
next?
So one more question. So in terms of the computer efficiency, so if you compare, if for example, if I want to solve a computer problem, the
Yes.
simple way is, let's say we use the classic naming theory, right? The
Right.
second one,
Right.
if I want to get the stress in the 6-inch direction, so what I can do is I use a three-dimensional element for each layer. Then
Yes.
I can get
Yes.
all the stress I need, right? So if I
Right.
compare
So
the computer efficient with the layer-wise theory, so can you give us a specific number of the difference? For example, 3 times faster or 5 times faster, something like that.
right. So okay. So there is one important thing. So in real world problems, we automatically, in a lot of cases, we have this so-called refinements. We try to put a more refined mesh in regions where we want more accuracy, right?
Yes.
So the same kind of thinking we extend to laminated structure. So the accuracy here is connected to the type of stresses that involve. So if you think of three-dimensional state of stress in some places, especially around stiffeners or around the holes, in those regions, you have to, refining the mesh does not do job because it still doesn't have the mechanism. So you have to use the 3D element technology. So that is where layer-wise elements are much cheaper, yet they have the same ability as three-dimensional elements. So you have to, in place of refined mesh, you will use a refined element, meaning element is a different kind. It's not the same plate element, but smaller elements. No, that won't do the job, because no matter how small you make the element, it does not bring the three-dimensional effect. Okay, so you have to use what we call global local analysis. Locally, you have to use very refined elements, means layer-wise type elements, and where the stress states are basically two-dimensional, that means interlaminar stresses are not significant, you can use the first order shear deformation theory.
Okay, thanks.
So that,
Thanks.
yeah, so that is a practical way to do it.
Okay, so here is a question from the audience. So the question is it possible for the layer-wise theory for more complex the architecture, for example, the woven textile composite material?
Right. Okay, so that's a very, very good question. Okay, so I have to remind people, if you attended my lecture yesterday, so we are engineers. We try to model the physics to the extent we think we can get the desired information. So if you have a textile laminated structure or textile composite, and still textile composites could be layered also, right? Or if
Yes.
they are not layered, you can imagine like they are layups. So that is where the modeling issue comes. So once you represent the woven composite as a layered medium, with each layer having its own properties, then layer-wise theory can be used. If it is not, if it is a single layer, the whole layer is all woven, then it is not possible for you to use layer-wise theory. You can use it, but one layer. But each layer, there is only one layer, so within the layer you have to do the 3D analysis, which is equivalent to saying that you are using 3D elements. So the layer-wise theory is only useful if you have a laminated structure with many layers. If you have only one layer, then there is no difference between the layer-wise theory and 3D elasticity theory. It's exactly the same. Okay, so we are not exploiting anything because there is only one layer. Okay, so to repeat myself, if you have a woven composite, and if woven composite is characterized or modeled as a layered medium, then you can use the layer-wise theory. Okay, and each layer will have its own architecture, right? And so, by the way, this is the same idea with architected materials now. So that
Thank
is
you.
the
Thank you.
metamaterials, all those are similar.
Yeah, we understand. Thank you.
Yeah.
One more questions. One
Okay.
more.
Yes.
Do you have questions? So if the audience don't have questions, I have one questions. So
Please.
from the layer-wise zero, right, we can get the accurate stress, especially the through thickness stress, right?
Interlaminar.
So yeah, for laminate.
Right. Right.
So for laminate composite material, one of the serious issue is delamination. So for delamination, we need the through thickness stress, right? So is it possible to extend your theory for delamination analysis? Because for delamination analysis, the discontinuity is invalid, right? So we need a single way to model this problem. So do you have any comments?
Right. Okay. So that is again a very good question. We have done that. What we do is, remember I talked about this phi function, phi through the thickness, phi of z, right?
Yes.
So that function becomes discontinuous function. So we will put a Heaviside step function wherever there is delamination. Okay. So the
Okay, okay.
delamination area would be represented differently. Elsewhere, we have continuous variation, even though it is piecewise continuous. But when you have a delamination at an interface, like I, at that point, you will have two displacements, one in the top layer, another in the bottom layer at the same node. So you have to bring the delamination, the discontinuity in the displacements. So it requires a little bit more effort, but it can be done.
It can be done, right? So,
Yes.
so if you do it, then what we can get is you will get weak stress singularity, right? Because the delamination. So how to treat this problem? Because if you use the stress criteria, the stress will be infinite. So how to treat this problem? You will use fracture mechanics or something else.
Right. Again, so you remember, for any type of prediction of delamination or crack growth, you need a criteria.
Yes.
Right. So that is not going to be different here. You still need a criteria. When does the node split? So that means you have to have a criteria for the stress exceeding sigma zz exceeding some value allowable. Then you say the nodes will split into two. Okay, and there would be two displacements. So
okay,
that means
I see.
you will
I
create.
see. It depends on the criteria you use, right?
Yeah. So but this is a good question. So you remember, you always need a criterion. It doesn't automatically say, oh, there is a delamination. So what that we need is either stress criterion or strain criterion, which will tell you if the material has failed and no longer taking the amount of stress. So we say if it exceeded, then we allow the node to separate into two nodes. So this so-called sublaminate concept also included in layer-wise theory.
Thank you. Let's have a break for 5 minutes.
Yes, that would be fine. So we'll come back at 9:05 or 9:06. Sorry, 10:06.
I think right now is 10, or in China it's 10 o'clock. We can come back to 10:05.
Okay, very good. Thank you.
Thank you. 我们稍微休息5分钟吧。我刚才时间没控制好，我以为是要到10点，实际上是10点开始。休息5分钟，我们10点05分开始。
Hi.
Hi. So you're working at home, right?
Yes, I'm at home. So you can see the Chinese picture in the background.
Let me check. 吴老师，吴真老师，这是你的研究方向啊，你得问问问题啊，这不是我擅长的。We have 2 minutes, less than
Yeah, no
2
problem.
minutes. Okay, so Professor Reddy,
Yes.
is it possible to implemented the layer-wise serial into the Abacus software?
Okay, there is an issue because they restrict the number of degrees of freedom at each node to only 6. So I think you can mimic in some ways, but I think you have to talk to the people and see if there is a way to do the layer wise in the context of 3D elasticity, because they have 3D elements. So
Yes.
somehow, so I think I have not explored that, but that is the interesting thing, because ultimately everything that we develop, we should be able to put into commercial codes. That way we don't have to develop all the other things. So we can utilize all the other things that are solvers, mesh generators, post processors, all of those are already in the commercial codes. So I think that will take some effort, but I think it's possible.
So because it is very efficient, right? If we want to solve a
it
computer
is.
problem.
In fact, I think see, the commercial people didn't invest enough in composites because probably they don't have too many users of composite elements. So what they do, they just use 3D finite elements. They don't
You mean
think
use
of
the global
layer-wise.
local method?
They leave that to the person who is modeling. They don't do anything special. They make the person doing the modeling to figure out how to use the global local.
Okay. So time's up. So let's start our second lecture.
Yes. Okay. All right. So what we are right there. So the second lecture is dedicated to the topic of finite element analysis of plates using the first order shear deformation theory. So I won't talk about the classical plate theory because that is no longer important in the context of finite elements, because the first order shear deformation theory can predict what classical plate theory can. So I will spend time in this lecture It may take a little longer because there is a lot of material, but I'll do my best to explain as clearly as possible. So this is the cover of my finite element book, 4th edition. But just to remind you that real world problems are very complicated, right? I mean, so all kinds of geometries, interactions. So when we think of modeling any of these structures, the finite elements is a natural choice, but the element technology that goes into finite element codes still requires uh, modifications or improvements. So like this reduced integration is really something we need to get rid of because it has side effects. So we must think of finite element technology to be improved in the years to come so that our predictions are much better. So I'm just showing, generic pictures that you may find uh, anywhere, all kinds of structures that you model. So now, what are the contents of this lecture? It starts with the weak forms for the first order shear deformation theory. So those are statements resulting from the application of the principle of virtual displacements. Then we develop the finite element models. If these are equations of motion, meaning time-dependent problems, we do in two stages. One stage is called semi-discrete finite element model, where we take care of the spatial approximation. Then in the second case, where we include time approximation and make the final full discretized finite element model. And then the resulting equations are algebraic, but they have to be solved for each load step, for each time step. Okay? So that means usually you fix the load and you compute the solutions for different times. And then for a different load, you carry this analysis again. Okay? So how do we solve the resulting nonlinear equations? So that is another topic that I will discuss today. And in the context of nonlinear equations, you need to determine the tangent stiffness coefficients. Okay. So then I'll show you some numerical examples. And my book on nonlinear finite elements is a very unique book. It's not that I'm trying to sell it to you here, but so there are a lot of good books on nonlinear finite elements, but they tend to be very heavy on just only description. They don't give too much insight or help in terms of actual formulations. So whereas my book is more textbook-like, meaning it helps you go from very beginning to the end, including deriving the equations, then implementing into computer and actually checking your finite element results with how with iteration they change the solution. So it's a very, very hands-on type book, and I don't think there is any book which does this type of thing. So it is a more written for the people who are interested in learning and writing their own finite element codes. Okay, of course, writing finite element codes is a useful exercise, especially when you are developing new elements or new material models, new ways of checking damage, and so it would give you enough room for developing these user elements for Abacus or ANSYS type computer codes. So it is always a good idea to have a strong background both in the mechanics as well as finite element technology. So the general idea of any problem like plate bending problem is to first know what are the governing differential equations. Or at least you need to know what is the principle of virtual work for that problem. If you know the principle of virtual work, you go straight to the weak forms because the principle of virtual work is indeed the weak form. Or if you know the differential equations, then you have to develop the weak form. So I do both in that book. So I show that both are exactly same. Okay. So then once you have these statements, weak forms, you substitute the approximations and you get the finite element model. So when I use the phrase finite element model, means it is a set of algebraic relations between the nodal displacements to nodal forces. So these are algebraic relations. And the number of equations will be same as the number of nodes times the number of degrees of freedom at each node. And you must, as I explained towards the end of yesterday's lecture, there is a duality. Means every component of displacement has its dual variable. A axial displacement has the axial force. Transverse displacement has a transverse force. So you will have this duality. And the algebraic relations are between the nodal values of displacements related to their dual variables at the same nodes. So that is the end product that we get out of the finite element model development. After that, just like any numerical method, you have to solve the algebraic equations to get the unknowns. And then you can do post-processing, that needs to be done in order to find either stresses or failures, any type of thing. So that is in nutshell, that's what we do in finite element analysis. Okay, so here is by the way, if you are not familiar, just please take it as something valid. See, this is what we call the principle of virtual displacements for a typical finite element of a plate. So there I'm showing the stress resultant NXX, NYY, NXY. These are already discussed yesterday. Those will have the corresponding virtual displacements associated with it. So this delta U, delta W are called virtual displacements. But you can look them as if those are the actually interpolation functions for those variables. And that's what exactly we do at the end. We replace delta U with the interpolation function.
Sorry, Professor Redding.
Yes.
Can you show your slide?
Oh, okay, sorry. Okay, let me see.
Thank you.
Hide presenter. Is this okay now? Yeah, can you tell me if this is better? Okay.
Yes, thank you.
Yeah.
Yes, it's okay. It's okay. It's better.
Yeah, yeah. All right, very good. So I'm sorry that I forgot to put my view off. Okay. So now you can see better? All right.
Yes.
Okay. So now you see the variables nxx, yy, xy, mxx. All of these are known in terms of strains, which are known in terms of displacements. So this is a very short way to write it. But if you express all of them in terms of displacements, the equations become larger, and I'm going to show you a few of them. Okay, so you can see that. So I separated now each of them into equations, but still they are in terms of the resultants, stress resultants. So you will have 5 equations because there are 5 displacements that are at each node. So these 5 equations will produce a finite element set of equations, which I will talk about that. But before that, I want to show you these equations that I showed you yesterday. The NXX, NYY, NXY, those are related to the displacement, including the von Karman nonlinear strain here. Okay, these are nonlinear parts. And you can see the A's, B's, and of course, we'll have D's when you talk about the bending moments. Okay, so all of these will be part of laminated problem or functionally graded plate. Either case, you will have the ABDs. And so the basic idea here is if you have a plate, now you remember even though plate has a thickness part is gone into our stiffness coefficients, ABDs, right? Then all we have is the midplane of the plate. So what you are seeing on the screen now is the midplane, which is arbitrary in shape. So I'm not saying it's a rectangular plate. It could be arbitrary shaped plate. And I'm using quadrilateral elements to represent the geometry. So I want you to know two things here. One, representing the geometry itself is an approximation in 2 dimensions. Okay, in 1D, we can do it exact because they are lines. But in 2D, it can have curved faces. So making the mesh refined will take care of the geometry representation. Then we also have to approximate the displacement field that I'll show you in a minute. So that would be another mesh. So in general, finite element analysis has 2 different meshes. But we choose, in most practical cases, same mesh for both. And this is what we call isoparametric formulations, meaning same degree of approximation for geometry, same degree of approximation for the variables. As a result, we don't show 2 different meshes. But in principle, you can have 2 different meshes. Okay. Now, when you go through the approximation of the variables, I'm showing here the degrees of freedom at each node would be U, V, W, phi x, phi y. So you know the 3 displacements and 2 rotations. And I want to remind you that U, V, W here are not the total displacements. Like in the layer-wise theory, U, V, W there are 3 total displacements of at a point. Whereas here, UVW in association with PX, PY become total displacements. Because you remember, the total displacement in the X direction would be U1 plus Z times phi X. So that means together they will produce the total displacements. Okay? All right, so UVW here are only the mid-surface displacements. They're not at an arbitrary point through thickness. So, but with the help of the rotation functions, we can find the location of the any point through thickness at any time. That's not a problem, okay? So that means we can gain 3-dimensional information from plate problems. But in most of the time, we don't seek that. We only try to find stress and strains and then use the stress strain information to determine failures. So at the end of the application of the principle of virtual displacements and finite element approximation, we get an equation like this, a structural dynamics equation, where M is the mass matrix, K is the stiffness matrix, which can depend upon the unknown degrees of freedom, especially the transverse displacement if it is von Karman type nonlinearity. So that means M may be a constant matrix, but K is not. K will depend on the unknown. So that makes it a nonlinear equations. So the structural dynamics equations are second order time differential equations in terms of the nodal values. Then we further approximate these dynamics equations to eliminate the time derivatives and come up with the equation shown at the bottom that is called fully discretized problem. So the difference is that the structural dynamics finite element equations are still differential equations in time. They're not algebraic. So we cannot solve them for unknowns. So you have to further discretize in time so that you get algebraic equations, which now can be nonlinear. So we need to solve them somehow, and which I will discuss in a few minutes. So the equation shown here, the S refers to the time step. Okay, so that means it only gives you solution at a particular time in the time history. You cannot get all of the solutions at once. So you have to march in time. You start with time t equal to 0 with initial conditions, and you obtain the solution for first time step. Then use the first time step solution that we know to determine the second time step solution. So that is the nature of time approximation. By the way, this is the same whether you use finite differences or boundary element method or any other method. So that is, the feature is the same thing. You cannot determine the solution at all times in one go. You have to only determine one step at a time. However, in static problem, we determine the solution at all spatial locations in one go. All of the nodal values we get in one go, right? But we cannot get all of the nodal values for all of the time. It is only for one time step at a time. Okay, so I hope I made that clear. Now let's go look at the approximation. So you remember we have 5 unknowns, U, V, W, Px, Py. So in commercial course, you will also have the 6th degree of freedom, which is the phi z, means a rotation about the z-axis. But that is not part of the theory. It is part of the need, because you want to also solve problems where the plate is folded or L-shaped. So then what we call rotation about x and y axis in one part of the plate becomes rotation about the z-axis in the other part. So you must need 6 degrees of freedom at each node to solve real-world problems. So, but for flat plate elements, you only need 5 degrees of freedom. 3 displacements at the mid-surface and 2 rotations about the x and y axis. So without going into the detail, when you substitute the approximation, so again, go back to the previous slide, you see the nodal values are functions of time. So that is important to note. Whereas the spatial discretization is going through the interpolation functions. So in my works, I use the psi, and like Zienkiewicz or other people, they use either N or L as interpolation functions. So I don't use N and L for the interpolation. I use the psi, okay? So, but that's just a notation issue. So when you substitute these into the weak forms, you get ordinary differential equations in time. So the U, V, W, Px, Py are columns of nodal values, but they are derivatives with respect to time. Okay, so this is the structural stiffness matrix. This is the mass matrix. And mass matrix, because of the way the equations are, only some parts of the mass matrix are non-zero. And of course, all the diagonal mass matrix is non-zero, which is a good thing. Okay, all right. Then we can, so I don't want you to read into anything here, but I just tried to highlight there are nonlinear parts which are shown in red. So the K matrices depend upon unknowns. So we have to necessarily solve numerically and evaluate the K matrices numerically. Because at each time, iteration, we assume the deflections are known from previous iteration, so that we can calculate the nonlinear terms based on the solution we know from previous iteration. So at the very beginning of the iteration, we assume the solution to be 0, so that the nonlinear terms drop out. So first iteration solution is the linear solution, which is also a good thing. This is the nice thing about structural mechanics, because structural mechanics always has a linear part, then nonlinear parts. So when nonlinear part is 0 at the beginning of the iteration process, you get a linear solution. Then you use the linear solution to evaluate the K stiffness matrices, that means the nonlinear terms, and then solve for the nonlinear solution from second iteration onwards. And I'll explain a little bit more in coming slides. So these are just showing you the stiffness matrices. So one thing that I want to go back, see the underlined in red? These are the terms that have to do with shear deformation. A45, A44, these are the transverse shear stiffnesses. And these are the terms that need to be evaluated using reduced integration to eliminate shear locking. Okay, so this is what commercial codes do. So then we, as I explained to you earlier, we convert the dynamics equation to the static equation, meaning fully discretized equations that are algebraic. So in going from the structural dynamics equation to the algebraic equations, you must use a numerical time approximation scheme. So there are many. And most popular one is the Newmark scheme. Linear acceleration, constant average acceleration, centered difference, and so on. So those are all built into the commercial codes. You have a choice to pick them, but some of them are conditionally stable and others are stable. No matter what time step you take, you get a solution that does not blow up, but doesn't mean it would be accurate. You still have to use a small time step to get a good accurate solution. Whereas other schemes which are conditionally stable, you are required to obey the requirement of stability, meaning which usually poses a restriction on the time step size as well as on the mesh. So that means if you pick a mesh, it dictates a time step. And if you refine the mesh, your time step will go down. That means you refined one will automatically doesn't become stable. It gets worse actually, until you make your time step even smaller. Okay, because that is the relationship in the stability criterion. Okay, so I just mentioned shear locking, and there is a membrane locking that comes because of nonlinearity. So both of them are eliminated through reduced integration. So all the terms that contain shear coefficients will be under-integrated, and all the terms that contain the von Karman nonlinear terms will be under-integrated. So those two will eliminate the locking, and I explained a great deal in my books, but we can read it. These are largely due to the lower order approximations that we use. So these are nothing to do with the theory. It is the numerical approximations that we use cause of this problem. So when you deal with lower order approximations, and then you say all variables should be equally treated with linear interpolation, then they will not really satisfy the governing equations correctly. So we have to use very refined meshes, or you have to use these tricks of reduced integration. If you use higher order interpolation for all of the variables, higher order, cubic, fourth order, then no locking at all. Okay, but it will involve more computational effort. And of course, that may be the best way to go, because then you don't have any side effects. Okay. Okay. So here is the discussion of iterative schemes. So after you finish with the full discretization, you have an equation of this type. K, the effective stiffness matrix. Now it contains the usual stiffness matrix and mass matrix inside. Okay. But it depends upon the unknown solution vector. And we are trying to seek the solution at time s+1. And for a fixed load. So what happens is we start with a known initial guess. And in the case of structures, initial guess could be 0. So you get a linear solution for that iteration, for that time step. And at the fixed time step, we go to the next iteration. So when you solve this, you get delta. That delta will be used here again. So I'm showing that here. I'm now calling S, because this is the element equation, this is the global equation. So the solution vector is U, and this U will be from previous iteration. So this equation tells you the correct story. That means U superscript R is the rth iteration solution for that time step. Whereas R plus 1 iteration solution is what we are trying to determine. And we know this, we want to determine this. So since we know this, we can evaluate the K hat. Okay? So this is similar, this is, by the way, is called direct iteration scheme, or sometimes called P-called iteration. So just a name. So here, there is no tangent stiffness matrix or any such thing. We just keep using the known latest iteration solution to update your K matrix. So that is equivalent to, I'm showing here in a one-dimensional system, if you have a single degree of freedom problem, Ku equal to F. So this U is unknown, this U is unknown. So you have the actual force deflection relationship like this curve, solid curve, which we don't know what it is actually. But for discussion purposes, I'm showing, suppose that is the curve. What the direct iteration does, when you start with the initial guess, that guess corresponds to a point on the load deflection curve. So you draw a straight line from the origin through that point. And wherever that hits your load vector. So FC is the load that you are putting on the structure. For that load, the solution is this solution, right? So to get there, we start with this initial guess. It will give you this solution as the first iteration solution. Once you know that point, now you draw another line to that point. It will give you this as the next iteration. So you keep on doing that, you will end up with this solution here, provided it converges. Because this, I took a curve which seems to make it converge easily. But this curve could be very complicated one that may make the iteration to go back and forth and never converge. So in that case, you have to really use so-called arc length method, and which is a much more robust but very complicated logic. And so people interested in that should read more. So I explained what direct iteration doing. Now we can talk about how to stop convergence. So we check the square of the difference between the solutions at any node with at two consecutive iterations, R and R plus 1, and sum over all of the nodes of this mesh. Then normalize that width, because this difference itself could be smaller than your specified tolerance. So that's why we normalize it. Then take the square root and check against specified tolerance, means error tolerance. It could be 10 to the minus 2 or 10 to the minus 3. Okay. So by the way, if we get two gradients at 10 to the minus 6, it may not converge at all. But it is really academic to say 10 to the minus 6. See, 1% error or 0.1% error means 10 to the minus 2 is enough. So you don't really try to unnecessarily force your code to go into iteration, and it only helping you get 4th or 5th decimal point accuracy, which is only academic. Especially remember my point yesterday, everything that we are doing is approximate, including your differential equations. They are not exact. Okay, so you have to have the right perspective about engineering analysis. Don't try to say, oh, I'm going to solve inexact equations exactly. What is the point, right? Okay, the next iterative technique is called a Newton's method. So before we stick this Raphson, Newton's method is based on expanding in Taylor series. So the Ku minus F is called a residual. So if you look at the equation, right, the residual would depend upon unknown Us plus 1. So now we say we will expand this function in terms of the known solution from previous iteration. So that's what we are doing. So the solution at R plus 1 is what is unknown, will be expanded in terms of UR. So Taylor series says UR plus 1 minus UR, then differentiation of this R function with respect to U, but evaluated at odd iteration, and so on. So this goes to infinity, but we truncate right here because after this, they are getting squared means nonlinear. So we stop. So this is what we call linearization. So when we stop here, then it is and force this to 0 because that's what we want. The residual has to be 0. So then this goes to the left side with a negative sign, and this becomes the tangent stiffness matrix. And this is the increment of the solution between previous iteration and current iteration, which I call delta U. So we are solving K tangent times delta U is equal to minus residual. And minus residual is same as the force imbalance. You see that? F minus KU. So the minute you get F minus KU to be 0, you solve the problem, right? So we are driving the difference between these two to the 0. So the tangent stiffness matrix is a new or additional effort you have to put in to determine for your this Newton's method. And typically, if you don't update this at every iteration, but only update every 5 iterations or 3 iterations, that is called Newton-Raphson. Whereas if you update every iteration, it is called full Newton. Okay. So remember, if you don't update the K, but you must update the residual, that you cannot stop doing it. Then you won't get any new solution. So you must update the residual, but you may not update the tangent matrix. Okay. So, but you still have to update after few iterations. If you never update it, you get a wrong solution, or it never will converge. So the definition of the tangent stiffness matrix coefficients is right here. So it's very, and those who are interested, you can read my book. I explain exactly how to determine them from simple problems to very complicated problems, starting from one-dimensional to beams, then to plates. So this is the kind of detail you will not find in any other books. So what is the difference between the direct iteration and Newton's iteration? Well, Newton's iteration scheme is a tangent that it is seeking. So if you start with the initial guess, okay, that guess is going to, for whatever that, this is the point, you are taking a tangent. So we are not putting a line from the origin through that point. We are drawing a tangent at that point, which is the tangent matrix. So then you hit this and you get that solution after the first iteration. Then you draw tangent there, so it will put you here. So you can see for the same curve, the Newton's method is much faster because it's going fast way to the solution. Okay, so for the same type of curve, as I just mentioned, you get better convergence for Newton's method. Okay, so the other thing that I think most of you should know is our interest in structural mechanics is to determine the strains and stresses after the finite element solution is obtained. So we go through this exercise of computing the derivatives of the various terms which are needed in the computation of stresses. So, but in doing that, we use reduced integration points. The reason is that the solution U is of some degree, but du dx would be lower degree, right? So that is why we have to use it, evaluate the derivatives at low order, because those are low order polynomials than U. Du dx is a lower order than U itself. So in the case of linear elements, we determine at the center of the element. These are master elements. In the case of quadratic element, we use this 2 by 2 Gauss quadrature points. And one can show through rigorous mathematics, these are the best locations for the gradient of solutions for any problem, whether it's stress analysis or not. Okay, so then we go to stresses. Stresses are related to strains through the constitutive law, and the Qij are the layer constitutive coefficients, which are related to the fiber direction modulus and then the modulus in the other direction. So these are the Qij. So once we know those, we can compute the strains. From there, we compute the stresses. And so the strains in the case of nonlinear problem will involve nonlinear terms as well. Okay, so I show a couple of examples, then we are done. Okay, so this is a simply supported plate. And I have to also say, as a remark, what we call simply supported in academic thing is probably not as meaningful in real world, because you must know what exactly you mean. So I showed, for example, two possible simply supported here. So what is the difference? If you look at the edge here, the edge parallel to x-axis, I'm saying UW px is 0. So now I want you to remember what is px. Px is a rotation about y-axis. Okay? Whereas py is a rotation about the x-axis. So look at this. Px is 0 means rotation of this edge about y-axis. Means we are not letting that edge to have a rotation in the edge itself. Means that we are making that edge to remain straight. Okay? It's important to understand. So, and whereas if I don't do that, then it is a different boundary condition. Okay? So the real world problems, you must try to understand how is it supported. And of course, every engineering problem requires some type of approximation. Approximation in the representation of the loads, geometry, and boundary conditions, and material properties. So all of these become very challenging. It's not, see, once you have that settled, solving the problem using computer codes is very easy because they're all there. It's just a question of writing or inputting the data correctly. So anyway, for the two different problems here, one where I have UWPX is 0, in the other case VWPX is 0. So in both cases, edge will remain straight, but in one case we are saying U means this way. The edge can actually free to move in that direction. Whereas in here, no, it cannot move in that direction. It can move along the x-axis, but it cannot move across. Whereas here, it cannot move along the line, but it can move across. Okay? All right. So with that, I'm showing the result here. A load parameter is some kind of non-dimensional load representation in terms of the intensity of the load applied. And the deflection is measured with respect to the center. Center is the maximum. And I divided with the total thickness of the plate. So you will see that the load deflection curve, so if you really do linear analysis, you get these straight lines depending on which boundary condition. You see that? So, but the curves deviate from the straight line just before 1. So what does it mean? That means if your total deflection of the plate, when it exceeds the thickness of the plate, then nonlinearity is going to come into picture. So this is some kind of guideline. So if you do any bending analysis where deflection is small, it's not equal to the thickness of the plate, you don't have to do nonlinear analysis. But if it is larger than the thickness, then it must be nonlinear. So you can see SS1, which is this, is much stiffer than SS2. So you understand the stiffness of a structure not only comes from the material, but it also comes from the thickness of the plate and the way you support the boundaries or edges. So SS1 is a stiffer type of boundary conditions than SS2, as you can judge from the result here. So the next picture is a circular plate. Okay, so here, of course, because of the clamped nature and uniformly distributed load, we can use one quadrant of it, and you can see the load deflection curve. This is just to show you, it doesn't mean you will apply the load all the way up here. You may be only in this region, 20. But even then, it's quite nonlinear, right? So if you draw a straight line, it would go along this line. So it will definitely, when W over H is equal to greater than 1, it will start showing nonlinearity. So this is a very good guideline. Every time you do linear analysis, you see how much deflection there is. If that deflection is larger than the thickness, you must know that you must do the nonlinear analysis. And another example I will show you is where I compare with experimental work. This is an orthotropic plate where the sides are 12 inches square plate. Thickness is 0.138. By the way, I'm using English system of units. You can always convert them to metric system. So as you can see, the side to thickness ratio, 12 over 1.138 is somewhere in the ballpark of 80, right? So that means it is a thin plate. But even if it is a thin plate, large deflection range, it can show the effect of shear deformation. So you can see the linear solutions are here, whereas the nonlinear solutions are here. So you can include this part, the one that is shown at the bottom is coming from the classical plate theory solution. Whereas the dark symbols are coming from the first order shear deformation theory. And the experimental is right above that. So the first order shear deformation theory is doing quite a bit of accuracy compared to the first order the classical laminate plate theory. So whereas in the early on, they're all same because the effect of shear deformation is not felt because it's a thin plate. But even though it is a thin plate, in the nonlinear range, the shear deformation is going to make the plate behave much more close to the real structure, whereas the classical plate theory tends to model the plate as a stiffer plate. So deflection is less. So that is the issue with the classical plate theory. Okay, so there are other examples, including even other types of boundary conditions. SS3 means all three displacements are confined. That means U, V, W on each edge are set to 0. So it becomes much more stiffer plate, almost close to fixing or clamped plate. Only difference is the rotations are not restricted. So here is the, I scanned this picture from the book. So this is for composites, 2-layer, 8-layer, and so on, because this allows you to see for the equal total thickness, but you subdivide the layers, it is going to behave differently because this is the beauty of laminated structures. Even though you may use same amount of material, how you lay up can change the stiffness of the structure. So anyway, this is one example there, and so more can be found in the book. Okay, so I want to close this lecture by saying that we started with the principle of virtual displacements to develop the weak forms for the plate equations. Then we did the semi-discrete finite element model. Then fully discretized finite element model means I did not go into the detail of the Newmark scheme, but I said Newmark scheme is used to convert the equations to fully discretize differential element equations. Then we solve the nonlinear equations using direct iteration or Newton's iteration. So in all my work, I typically use the Newton's method. I don't use the direct iteration because typically direct iteration takes more number of iterations, at least for the structural mechanics problems. And then I briefly discussed about the tangent stiffness coefficients. And then I showed you some numerical examples. So I'm here to take any questions, and I think we are okay, right on time. So I have a couple of closing remarks before I let you ask questions. So I'm always of the opinion and advice to younger people saying that you should always think of mechanics as the foundation for anything you do, because you cannot just only think of numerical work. You must always support your findings on the sound mechanics concepts. Means you have to have a strong background in engineering subjects, whatever that field you're in, heat transfer, fluid mechanics, or structural mechanics. And if you're specialized into composites, you should know enough about composites. If you are into even subset like woven composites, you should know enough about it. You should not just think of, oh, I'm going to just model it. So models you develop, they are always based on some assumptions. So you must make sure that model is capturing what the actual structure is model representing the response. So it is important. So that is where the mechanics comes in to help you understand the physics. Okay, so it is important to know whether the mathematical model is good enough for predicting what you're looking for in your analysis. The other thing is we must continue to develop or modify or improve the computational tools. So the improvement come in a number of ways. One way is to improve the computational technique itself. So that means you find ways to get rid of any kind of artificial fixes like reduced integration. The other way to improve computational model is to modify the mathematical model, such as going from first order theory to third order theory or third order theory to layer wise theory. Because you are improving the mathematical model means physics being improved. Okay. But in all ways, engineers look for simplicity, robustness, and practicality. Because so the simplicity means we don't want to burden ourselves to solve problem. We don't have to go through enormous computational effort to get the results that we need to start the preliminary design. So robustness means whatever fixes you use, they should be good enough for all types of problems, not just good for one problem but not the other. Practicality means you should be able to compute things in a reasonable amount of time. Because most of the time, your manager, if you work for a company, they want you to produce the results very quickly. So you must always think of, are you able to do the job in reasonable amount of time? So that means you have to balance your effort between all these things. We also must conduct physically meaningful experiments, because some of these experiments will help us understand if our computational model is doing right. If the computational model is not doing right, then we have to go modify the mathematical model and allow for the mechanisms that are missing. So that is very important. So the challenge for the mechanics people like us is to understand the technical problems facing the industry. So most of the time we are more interested in publishing, right? Because especially if you're in an academic setting. I mean, again, I'm not criticizing. I did enough of that myself. But I think it is also good for us, both in terms of feeling good that we are doing something to help industry, and also understanding their problems also may open up new areas of research and also facilitate funding. Because if you work on problems that facing industry, the industry might fund it, and the scientific agencies also see that you're trying to help the industry. Of course, these are high-tech problems, not just consultancy type problems. So you have to only take up, in addition to consultancy projects, you should take the problems that are long-term. That means basic research that have technological implications. So by doing that, you are also helping the society that we live in. Okay, so I'm going to close by displaying all these books, but it's not to sell them, but I just want to say there is so much to do and so little time we have in our life. So, we spend a lot of time. By the time we get to do some contribution, we already halfway through our life, or at least 1/3 of our life. So you should never underestimate the value of the time. And my advice to young people is to stick with topics. Don't move around too much. Then you're not able to contribute significantly to the field. So staying with a field of research for a long time will help you understand better and make contributions. So all these books I've written is with the interest to facilitate your learning and also provide tools for others to apply and advance the field of research in whatever field they are working. So it's not just writing the books for the sake of writing, but help others along the way that they understand these concepts and take on to solve engineering problems that they come across in their professional life. Thank you for your attention, for attending my lectures. And of course, I want to thank again Professor Jan for the invitation to present these lectures in this summer school. And I'm here to address any questions.
Thank you. Thank you. Very good talk, very good lecture, and very good, excellent conclusion remarks. So any questions? So there is a questions from the audience. The question is for the first lecture about the likewise theory. Is it possible to apply it for the plasticity?
Apply to what?
The layer-wise theory for plasticity.
Oh, okay, yes. Okay, so that is in fact even better there because, the plasticity grows, by layer. So it's even better there because if you have a single layer theory, you still have to create a layer type mathematically, create a layers because, for example, think of bending. The bending of beams, the plasticity grows from the top and bottom, right, toward the center.
Yeah.
Because the
Yes.
stress is large at the outset. So you have to kind of subdivide through the thickness. That means you divide the height of the beam into layers. So the layer-wise theory is even much suitable in those cases because you can assign which layers, which elements in the layup are already plastic. So it is definitely a better thing. And in fact, I would say in general, even if it is a homogeneous beam, when you do plasticity, it is really more like a layered medium because the plasticity is growing by layer.
Okay, thank you.
Sure.
So go. I mean, it's for the you actually have give some good suggestions. Actually, I still very interested in why you get so many achievements. Do you have some secret? Can you share with us about how you get so many achievements, especially for the young faculty like me and the master students? Actually, you have given some, but could you share some more?
So I have to be very frank with you. There are several things that that happen. One, of course, I do work very hard, but working hard is driven by the passion for learning and doing. Then I have to give a lot of credit to my students and collaborators. So especially in the last few years, I have a lot more collaborations, including people from China, Hong Kong, Portugal, Spain, all over the world. People want to work with me because now they do the work, and I only advise them on ideas and sometimes derive few things here and there, but they do the work and they put my name on it. Okay. So I have done enough of my own things over the years, but in last few years, it's much more productivity due to the collaboration with others. So I think I'm not trying to say everybody should work like me. In fact, I would say I'm not a real role model for that because real world requires a balance. You have to take care of your family, which I did only as needed. Okay. And probably you have to balance between three things. One, your family. Second, the work. And third, society at large. But you never distribute your effort equally between them. It never happens that way. So you sometimes spend a lot more time for family because you are needed than at work, and vice versa. But we also know every day we spend majority of quality time at work, at least 8 to 10 hours, right? So it is important that you also enjoy it. You feel that it is something exciting. If you don't have that feeling, it becomes boring. And you are only looking to the clock and see, oh, when I'm going to done here, I will go home. So I think that is not the right kind of feeling you want to have. You want to enjoy what you do. And that enjoyment comes by creating a sense of, research is a mystery, actually. When you find something, then you get excited. Oh, that's what's happening here. Because most of the time, you don't know the end result. So anyway, I try to say in few words in my own way, whatever I've done, it is credit goes to a lot of people, but I am also putting myself in the equation by saying if I don't have interest, these things don't happen. So I have to have interest. So in fact, I say there are three things that matter in a human being's life. One is you yourself. How hard you work, how passionate about the research or work you do. And second is the people around you. That could be your friends, your teachers, your spouse, your parents. All of these are really doing their thing. And it is always important to take a moment to thank them on occasions you find. Never take anything for granted. They are not doing to expect a thank you from you, but they are doing it. So you must thank them. And third, you probably won't expect that, but is a luck. The word luck is a combination of being right place, right time, something happening, in your favor. So that element is always there. So, but I always tend to say luck is going to come your way if you have the first two. Okay, that means you put your effort, you are the one doing the work, and with the help of people around you, you will be favored by luck.
Thank you very much for your suggestions and your comments. Yes, Yes, well, I actually am very interested in your lecture and your comments. And also, I have one more questions, which is related to the structural mechanics. You know,
Okay.
you are work on structural mechanics or let's say applied mechanics, right? From the
Yes.
academic, there are very few person who have interest in structural mechanics because it's just very old and something like it's old, right? And it's not easy to publish the high level papers. So for these persons, it is very difficult to survive in the academic. So do you have any stress for these young faculties?
Right. I think, again, this is not a easy thing for me to address because I do feel very concerned and sorry for young people because there is a lot of pressure put on them to publish, bring money, advise students. And there are many more people doing the same compared to when I started. So it's only getting more difficult because there are same amount of money, but more people are wanting to share that money. And same way, there are topics that are, few topics, and everybody wants to work in those areas, especially those areas that they think are very hot, nano, bio, and so on, right? So I think it is always good to find an area that is not crowded and then you stick with it for a long time, long enough to make a name for you. So you have to have a bit of patience. If you are in a hurry to publish and get famous, it won't happen. And so I think there is a part of for this what do you call planning and executing right way. So planning in terms of what are the areas that are really fitting to your background and interest and how many people are exploring this area. If there are too many, you will have a hard time to publish or even make a name for yourself. So it's a kind of tricky thing that you need to evaluate the field by looking around and finding ways to minimize the competition. So this is itself is a, I think, research for you.
Okay, thank you. Thanks.
Sure. By
Thank
the
you
way,
very much.
I'm going to give a general motivational or advice type talk on 11th of August about this time, about the time that I gave the talk, first talk today. So I will send your email to you and you might share with younger faculty colleagues. So most of the things I will say would be to help young people on, with few things. So it would be just a 1 hour lecture. And so that's what I'm planning to do on 11th of August. Okay. So please tune in. I'll send you an email with invitation.
Okay, thank you very much.
All right.
Thank you. So if
So
there's
if you
no
don't
more
have any
questions,
questions, I wish all of you a very good morning and rest of the day and life in general. Okay. Take care and stay safe.
take care. Thank you, Professor.
Yeah. Bye.
Bye. 那我们今天的这个就